Let's see. Okay, this wants to connect Pro. Okay, there's still some folks missing there. Well, I have to tell you that I'm not 100% today. In fact, I'm probably under the influence of medication. And I'm on my back, comfortably resting. So I don't think I can pull off a lecture today. But what I want to do is the test, the project, and see if you guys are and I am on the same page with respect to that test. I have actually prepared what I call the template, and I didn't send it to you guys. And part of the reason for that is I get very little feedback. There are very few people who ask questions about this project or test, and I'm not hearing anything from the rest. And there are two possible reasons for that. Is number one, everything's under control so much that you really don't need any questions or any help. The other option is some of you guys are giving up on me. That I'm not able to help you in any way, and you feel that that things are not going well. So let's see if we can get you interested in this a little bit. I still see that there are only 5 folks there. Don't know if others will join later or not. But one thing that I noticed from somebody's file, the strength constraint is unlike what we did in the tutorial. And this probably was the major difference of this particular problem compared to the tutorial that I did for sequential linear programming. And the major difference is the tutorial that I did in the sequential linear programming was based on max strain, or almost equivalent to max stress constraint, which meant that actually for each layer there were 6 separate constraint equations, one for each stress component. So for a layer that has 0-degree plies, for example, there were 6 constraints that limited the max strain in tension and compression along the fiber direction. That's 2. Transfers to the fiber in tension and compression. That's 2 more. That's 4. Total of 4. And shear, plus shear, minus shear. And that's another 2 constraints, meaning that there were total 6 constraints per distinct ply orientation. And if we did 4 different ply, distinct plies, 0s, 45s, minus 45s, and 90s, that's 4 times 4. And that's a lot of constraints. Now, in the case of test 1, you implement the SI Hill constraint that is one constraint per ply. Okay, and if you have a 0 and a plus 60 and a minus 60, there are a total of only 3 constraints. And so this is actually a fairly simpler than the tutorial that we did. If you could actually see how the failure constraint is implemented. So that was the part that you were supposed to be spending your time. Now, any questions about this? Any comments about this? Speak up, please. To be honest, I was lost. Oh, disappeared. Okay. Okay. So what I want to do now, Edison, is actually show you my template and start going through it for this template. And of course, if you keep going and going and going, it's no longer template, but it becomes the solution file. But I'll try to, give you some room for experimenting your ideas. The thing about this is, I think you should actively try to see if you can on the side compare what you have been doing with the template that I'm showing, and the order of some of the executions are not very important. But I will tell you one particular importance where sequence of some executions will make a difference, and that is the use of the parameters m and n that control the number of plies to be left as parametric variables rather than numbers. So every time solving the problem for 1m and 1n from beginning to the end, if you leave those parametrically and the optimizer starts putting m and n as it goes, it'll make a big difference. It will be the correct solution. So this is something that I'm going to emphasize, and I hope you're going to be paying attention to that. So are we in agreement that I start going through that the template that I have? All right. Let's see. I don't have two screens in front of me. I have only one screen. So bear with me. And if halfway through, if I fall asleep, somebody scream really loud, I have my headset and I will wake up. All right. Let's share my screen. Okay, I can get rid of that. All right, this is my test 2 template. Let's quit kernel. And popular mechanic is telling me something. And output. All right. So the first thing I'm going to do is I'm going to run my CLT program. That's my CLT program. Run all code. Okay. Ran all my code. All right. So this is a test 2 template. As usual, check first if the composites is available. It is, since I ran the thing. The first thing that I'm doing in the template is specifying some of the constants to the plies. By the way, please do check my numbers with the ones that you've been using to make sure that we are all on the same page. So the ply thickness of 0.125, 10 to the minus 3. And material that I'm using is 204, 10 to the 9, 18.10 to the 9. These are obviously giga. I think they were metric Pascal. And the strength that I'm using is this. We'll talk about this a little bit later. This is fiber reduction, tension and compression, transverse tension and compression, and shear 10 to the 6 mega. So I'm going to execute these. So these are the values that I'm using. Right. I may have changed my sequence of use of M and N. I built this later on. I realized that typically I prefer M for zeros and N for 90s. So my M integer and N is integer. M will have M times 0 degree layers, and then the N times plus 60, and N times minus 60, and then I reverse it and add the rest. So if I have a 2, 2, it will have 2 zeros, 2 plus 60s, 2 minus 60s, and mid-plane symmetric. So this you may use your own. It doesn't matter. As long as you're consistent with this, you should be okay. So if it was 1 and 1, 1, 0, 160, 1 minus 60, and then mid-plane symmetry, minus 60, 60, 0. Then I use this A matrix construction that allows me to actually put the ply thickness of each layer in a separate T vector. And instead of calling the A matrix with one thickness, I call it with a T vector, which is the vector of thicknesses for individual plies. So this is an important upgrade to computation of A matrix. And I defined a new function for this, calling it my A matrix, so that I can compute it once with symbolically M and N, simplify it and store it in A matrix. So depending on what A matrix my optimizer wants to evaluate as it changes M and N, A matrix will give me the right answer. And that one is this. So this is A matrix as a function of M and N. So if I were to type 1 and 1, this would have been the A matrix for M equals 1, N equals 1, all numbers, okay? But right now this wasn't assigned to anything, so I'm just going to actually delete this line. So my A matrix now has a form that M and N are parametric in there. And my objective function is n plus 2 times n times ply thickness times 2. That's the total thickness, which is only a function of m and n. All right, so these are the design variables m and n, objective function, and A matrix. Now I need to do the analysis, and I need to do the analysis of the baseline design. So baseline, I'm going to take m equals 1, n equals 1. and I'm going to do the analysis for it, but I can always do it for generic M and N first, and then put the M and N values. NX, we're putting 4,000, and Y 4,000, and XY 0. Is that correct? No. I don't know. What was it in the problem statement? Okay, there's a ping. Where are you? Since I have one screen, I don't know where you are. That should be on Safari, right? Safari. And next is 1,000. All right. Yeah, so this statement is nonsense in the template. And I'm going to define NX bar to be 1,000, 10 to the 3, and load N, NX bar, alpha times NX bar, beta times NX bar. All right, let me see. There's another ping I need to look at. All right. Okay, Alex says I'm also using a different stacking sequence, plus 60, 0, minus 60s. Okay, Alex, that should not make a difference. Since we are doing in-plane problem, there is no bending in this. The sequence of these plies is not going to make any difference. In fact, even if it has 150 layers, I'm just going to do the analysis for only 3 layers. One for a 0 degree, one for a plus 60 degree, one for minus 60 degree. That should cover it. Mary says NX. Okay, NX, yes, alpha 1, NX beta times beta 0, 1. Yes, that's actually what I just discovered. That is very good. So NX bar, we specified it to be 1,010 to the 3. Load NX bar, so that goes in here. Alpha times NX bar with times NX bar. So the load vector is 1 million times alpha, million times beta. Was it really 1,000 or 10 to the 3? Did I make up again something here that is... Okay, all right, very got it, thank you. All right, so load is defined, load vector, load N. 2 more parameters, alpha and beta. I'm going to leave it parametrically because then I can substitute load cases and compute for any load case that I want. Now, the next thing is to find the mid-plane strains of the laminate. And this requires inverting the A matrix and dotting it with the load vector, NX, NY, and XY. And note that inverse A matrix is going to actually invert the A matrix parametrically. M and N will be left there as parameters. So these are mid-plane strains of the entire laminate. It's a fairly long expression, but nothing that, in fact, if I use chop, some of those zeros will disappear without influencing the rest of it. So these are the mid-plane strains. And if I want M to be 1, N to be 1, mid-plane strains are now only a function of alpha and beta. Okay, and if instead this had 3 layers of zeros, and these would have been mid-plane strains. So you can see that as the laminate gets thicker, this number is becoming smaller. Let's put 1 again. And the influence of alpha also changing, but in any case, this is just a demonstration. This is not a scientific value anywhere. Mid-plane strains is still parametrically defined as this cell here. Then we need to go to layer stresses in X and Y direction. So we need the Q-bar matrix. And for the Q-bar matrix, again, as I said, I'm interested only in 3 layers. This is only A matrix. I don't have to do the entire laminate. I define a laminate here, which has 1, 0, 160 minus 1 minus 60. And this will be the Q-bar matrix for each of those. So the first is the Q-bar matrix for the 0, which is this number here. Second is the Q-bar matrix for plus 60. That's this one here. And this one is for the minus 60. As you can see, 1, 1, 2, 2, 1, 2 terms are the same. The only difference is the minus in the 1, 6 and 2, 6 terms that are different. All right. So I have 3 Q-bar matrices. If I dot the mid-plane strains with the Q-bar, I get the stresses in the 0-degree ply, and that's Q-bar 1. Stress, laminate stresses in the 60-degree, that's S, and minus 60, that's Q-bar 3. So mid-plane strains were actually parametric. Now I multiply those with constant matrices. I get stresses in the plate coordinates, again symbolically. Long expressions, this is stress in the 0-degree ply, stress in the 60-degree ply, and stress in the minus 60-degree ply, but in the plate coordinates. Then I need to go to layer principal material direction stresses. And for that, I use the transformation matrix, T matrix, again for the 0, 60, and minus 60, 3 transformation matrices. Those are also constant matrices. And if I multiply that with the 0-degree, 60-degree, and minus 60-degree with 1, 2, and 3, I get stresses in the principal material direction for 0-degree layer, stress in the principal material direction in the plus 60-degree layer, and the minus 60-degree layer. All parametric. And I actually put semicolon there and didn't show it there because I want to show them in matrix form. So this is stresses in the principal material direction for the 0-degree, 60, and minus 60. And this is it. So lengthy expressions again, but it's not too bad. There's alpha from the load case. There's m's and n's. And this is for the 0-degree ply stresses in the material direction. This is the first stress component, second stress component. This is second and third. There are 3 lines in each case. So this is sigma x along the fiber direction. which should be same as the principal material direction before transformation. It's only 10001 with that. So if you want to see that, it should be up there somewhere, this one. So for some reason, this and this are the same. So these are the principal material directions. So if you want to do the analysis for a load case 1 through 3, I define 3 load cases. Load case 1, when alpha is 0, beta is 0. Load case 2 is when alpha is 0.3, beta is 0. And load case 3, alpha is 0, beta is 0.4. And if I take psi hill and put m equals 1, n equals 1, and put load case in there, these are the stresses that I'm sending into psi hill failure. And this is going to produce only one number. This is one number for the 0 degree ply, and the strength is given here. And that's 7.56. So way too high violated. Okay, with 1 and that's 0 degree ply. G ply load case 1 for the 60 degree. This was for Z0, G ply 0, G ply 60, and load case 1 again, 14, G ply minus 60, and same load case. These are the cycle. If you wanted to do the load case 2, you can do G ply zeros, load case 2, G ply 60, load case 2, G ply minus 60, load case 2. This is also violating. And the third load case, G ply 0 degree, again, G ply 60, G ply minus 60. So these are, again, violations. And this time, one of the minus 60 is violated the most because there's a shear stress applied as well. So this is the stress analysis, all the way to the evaluation of the failure. And as I said earlier, there's only one constraint per ply. That's G ply Z for 0, G ply S for 60, G ply minus 60, MS for minus 60. Baseline design, I don't know why I changed it. What? What on earth is happening here? This shouldn't be here, this Okay, let me see. Somebody knows what I'm doing or what I'm doing wrong. That looks like tutorial 10. Yes, that looks like tutorial 10 to me as well. It's true. Very. I thought I went further than this. Okay. Yeah. We're gonna still do 1 M and 1 N. Let's see, let me get baseline. That's of course this is immaterial because I'm not assigning anything new to anywhere. I thought I went further than this for this. Let me hold on a second. What is going on here? Oh yeah, P1, P2, P3, they're all nonsense. It looks like either I left something in there that shouldn't be left in this tutorial, or after I actually changed it, my tutorial, oh my goodness. Yeah, I didn't save. The old file got stuck at the end of this. That is painful. All right, so that means I'm gonna go a little bit further with this. So we're gonna do, yeah. All right, total T0, 2 times supply thickness times M, which is correct, 65, 2 times supply thickness times N, and minus 65 is no 90. So these are the parameterized version of I'm gonna send this to you guys afterwards. So T0, 0 is T0 when M goes to 1. I don't know why I decided to use baseline as 1, but T60 base is T60, and T minus 60, the next 0 says means that it's the baseline. All right, so T0, 60, and minus 60 baseline values are these. There shouldn't be any change in the derivative calculation except the fact that these are now zeros and 60s. I wonder if I saved it someplace else. Let me save this, because I know I did this for the template and all right, Matthew, let me check what I did. Where did I do that wrong? Oh, TM60. What is 65? Are we good? I hope so. Thank you, sir. All right, so the derivative is basically given by this expression. We will need Q bar matrix, but the Q bar matrix has already been computed. Let me see, QB1. Yep. So there's QB1, QB2, that's 60, and minus 60, QB3. Okay, that's good. And just in case QB4 doesn't exist, very good. So my Q bar matrix already computed, just to show that it's there. I again need the inverse of the A matrix. So just to make sure that it's still there, yes, it is there. Inverse A matrix. So now apply midplane strains with respect to TZ. Limit midplane strains with respect to T60 and minus 60. All right. So this is the equation that says minus A inverse Q bar epsilon naught. That's this. So these are the derivatives of strains with respect to flight thicknesses. Which are now available. Now we are supposed to be getting into the nitty-gritty. I don't think I need to do these. This kills me. Where did I? Let me check if I actually stored it someplace else. If I did. Oh, no, there's only one file. So I did prepare the template, and apparently I never saved it and turned off my computer and lost that part of the solution. All right. 1, 1, 3, 4, 5 solutions. Oh, let me check the tutorials. It's March 23rd. That's an old one, so that cannot be stored in there by mistake. Yeah. One of typical things that I do, like writing emails and not sending them. I did a solution and then didn't save it. All right, let's see if I can do it again. The thing in the linearization is now there is only one of these. There is no P2, P3, P4. So those things should disappear. That should give the same thing as these. So none of that is interesting. And to get the principal material direction strain derivatives, we use the transformation matrix. But this will be 0. -60 minus 60, 90. Respect to z, huh? What did I do? All right. 60. Principal material direction, partial midplane. Principal material z with respect to f should become s minus s with respect to 0. Okay. Then I'm basically trying to erase and redo it again. Eliminated. This is partial with respect to z, partial with respect to 60, and minus 60. And this with respect to 90, which is also eliminated, so I can get rid of those. And the first three are corrected. Z 60 minus 60, Z 60 minus 60, Z 60 minus 60, and with respect to 60, 60, 60, with respect to minus 60, minus 60, minus 60, and it is 60, and it is 60, 60, and 60, and they are multiplied by, with respect to 60, 60. Okay, everything on the right hand side should be available. Everything on the left hand side are being defined new. I hope I didn't leave any typos. Please do check one more time. The first three are the derivatives of 0, 60, and minus 60 with respect to 0. Second three are derivatives of z 60 minus 60 with respect to 60. And the third three, last three, are derivatives of 0, 60 minus 60 with respect to minus 60s. Okay. So I have expressions here that look normal, no strange characters, undefined words, or anything like that. Hopefully, this is this, minus 60. Long, very long. There are 9 of these. but it is okay. All right, now we came to the construction of the of this. So in our case, here these equations are not correct anymore because there are no PQs and Rs. There is G, which is the Psi-Hill constraint, and it's just Psi-Hill minus 1 must be less than equal to 0. And then the derivatives of those, here it's just the strains in the principal material direction, but we just send into these the Psi-Hill numbers. So the constraint on the 0 degree layer, GZ1L, there is no more 1, 2, 3, 4, 5, 6. There's only 1. So GZ this is for I'm going to also put TH. I didn't use that in my previous solution, but just to differentiate the G Psi-Hill. This should change to the value that we evaluated before, which is the Psi-Hill number for the baseline design, which is T0. And that one, I think I may want to condense these things so that I don't see them individually. And I may want to also condense these. All right. Where did we evaluate? Yeah. G ply Z under load case 1. I'm just going to do the load case 1. G ply of the 0 degree under load case 1. So this is my constant for the question is, do I want to actually this is also parametric. I want to create parametric version of this. I think that'll be better if I do. So this is what I'm going to do. I'm going to copy this line. Oh, I can't do this. Psi-Hill will not take parametric. Yeah. Now I know. Now I know the reason. So these have to be executed before each run of the loop. So load case 1. Copy all these cells, and I will explain what I mean by this. These equations are not valid anymore. This needs Psi-Hill. And this has to be also replaced. this is the part that you're going to be somewhat busy with. All right. So the approximations. First of all, let's say we're going to be doing load case 1 for this iterations. I'm going to take these I'm going to merge these into one cell. Isn't it supposed to group them? Cell properties over deployed. Grouping, merge cells. All right. And I'm going to actually execute these without exact same thing. I didn't do anything different, but I know later on, as I reach different values to create different approximations, I'm going to have to change M and N, because I cannot send non-numeric values to Sci-Hill. Sci-Hill has to produce a number, so it takes only numeric stress values of principal material stresses in the 0, 60, and minus 60 layers, and produce the baseline value. So there are 3 numbers that will come out of this. I didn't show them. And the first one is going to be this. And there is no second and third and fourth and fifth. These all go. And then the G60 Sci-Hill. Actually, I should put L to mean the linearized version. And this one will go in here. And where's my cursor? Come on, cursor, there. These rest is going to go away. We're going to change these some more, so don't worry. And G minus 60, Sci-Hill linear. And the third number as a constant will go there. And no more of these things. And no more of the 90s. Okay, so we are approaching. So these are the new linearizations. The constants part are done. Next part, this has TZ minus TZ0 times PQR. They cannot be any PQRs. So we're going to change this to something else. Okay, and these should be the derivatives of the stresses with respect to because ours is stress criteria. So I'm gonna delete this and put capital XX. We're gonna have to figure out what that capital XX is gonna be. And T, all right, 60 minus T 60, 0. This is also a number, and this needs to be figured out. And T minus 60, come on. T minus 60, 0 times that capital XX, and there is no 90. All right, so linearization is basically linearized Psi-Hill. The Psi-Hill number for the baseline design, T0 minus T 0, 0. Unfortunate choice of variables and things. T60, TS 0, initial values. T minus T0. This is Ti minus Ti 0. And I changes from 0 to 60 to minus 60. And the XX is going to be, since I'm actually computing stresses, these should be not strains, but the derivatives of the stresses. Did I compute derivative of the stresses? No, I only computed derivatives of the strains. All right, so we need to convert them to stresses. Okay, so let me see. Can you repeat what the XX is? Yes. The XX is what multiplies T minus T0. And this is, there are no P's and Q's and R's. In the old constraint, the constraint was on the strains. So G baseline was a strain measure, not Psi-Hill number, not a stress number. So we need to replace this, something that actually have the Psi-Hill derivative of the Psi-Hill constraint. Okay, so this was the Psi-Hill constraint evaluated there, and this has to be the derivative of the Psi-Hill constraint. Now, to do that, the stress, the derivative of the stresses, and when you do that, you get numbers derivative in there. That's what it should replace there. And to do that, let me see if I can actually show you how to do that as well. What did I do last? Okay. So this is evaluated. This is GZ, GS, GS, okay. And I said capital X, but we'll see. Actually, we'll have to put different things in there. Where is my cursor? Okay, there it is. Come on, why do I not see? All right, so Sahil Z linearized, Sahil 60 minus 60 linearized, G ply 60 load case 1, load case 1, load case 1, and they come from here. So these three numbers come from above. T minus TZ0 comes, one of them is a parametric variable, the other one is actually a number, and they are down here. TZ, TS, TMS, those are numbers, and T60, TM, those are in terms of M's and N's. So if I actually execute this line, ignore them right now, but if I execute this, what you see is there's a constant, there's some constant with M multiplying X, some other constant with N multiplying this. So these are the things that we need to now figure out what they are. Okay. And those are the derivatives of the Sahil numbers with respect to zero-degree ply derivatives and 60-degree ply derivatives. You know, this is maybe type this X, Z, X, Z, X, Z for the first, for the time being. And this is for the 60, XS, XS, XS. And this is derivative with respect to the 90, X, minus 60. All right, so let's make sure that the rest is correct and constant. All right, we're not done yet, so we need to find what these x's and xs's and those are, and those in the original case derivatives of the strains, because that was the strain constraint we had G. Now we have the Sahil constraint. This is all these three things are going to be merged into one. So there's only one of these. That's why I said XC, XC, and XC. And XC is the derivative of the Psi-Hill constraint with respect to a change in the 0 degree ply. And that we have the principal material direction strain with respect to 0 degree ply. So we're going to actually send these in instead of calling the Psi-Hill subroutine with stresses. We're going to have to call it with stress derivatives. That's the only thing. So these three are going to go into, I guess. Okay, first we have to compute stress derivatives. So, what is stress from the strain? There's an equation for it. The only thing there is you have the equation for stress equals something times strain. That something is constant. You put strain derivative to the right-hand side, you get the stress derivative on the left-hand side. So you get stress derivatives. Once you get the stress derivatives, you put those stress derivatives instead of stresses into the Psi-Hill. It gives you Psi-Hill derivatives. And those will go into these x's, y's, and xs's and x minus s's. So this is how it will produce. So, question is, do you have enough to finish this tonight, or do you need to work on this more than just tonight to get these? I mean, I can write what you need to do, but that's part of the now homework assignment or the test assignment. That the derivative, these are the linearization of the Psi-Hill constraint. So this part, Psi-Hill numbers at the base design, which are evaluated here. This one, and this one, with respect to each of the thickness variables. Now, this part is summation I from 1 to 3. That's T0 minus T00, T60 minus T6000, T minus 60, T minus 60. Those are there. The only thing is this number here, these three things are replaced by one thing. This thing is replaced by one thing. And that one thing is the derivative of the Psi-Hill number with respect to first design variable, second design variable, and third design variable. So you're going to call the stresses in the 0 degree ply with respect to these variables. So this may come as very confusing, but it is not. If your computer module, Psi-Hill, gets 3 stress components and 3 strength values, computes one number, you don't change the strength. Strength is the same. But instead of stresses, you can send the stress derivative of first stress, and you get the derivative of the Psi-Hill number with respect to that. So you're going to have to call the Psi-Hill number at least 9 times to get these numbers here. Note that this Ti, thickness of 0, I when I equals 1. thickness of 60 when I is equal to 2. Thickness of, this is derivative with respect to thickness. So each one of these, now I wrote xz, 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 but you're going to see actually these will also change. In fact, this will probably become like this, more like 60 minus 60. And 0, 60 minus 60, because this is multiplying the 60 degree. So this is the derivative with respect to that particular, this and this has to match. Okay, and then this one is the there will be one Psi-Hill number and stress that goes into it will be the stress of the baseline design, its derivative. So xz, 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 xs, 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 minus s, minus s, minus s. S seems to be right. It's not quite clear whether we'll have to actually, this is Psi-Hill number for the second ply. So something has to be different for this one. So first ply stress Z ply Z ply Z ply, and then this will become 60 ply 60 ply 60 ply, and then this will become x minus 60 ply minus 60 ply minus 60 ply. All right. Looks like you're going to have to call Psi-Hill number 9 times to get these 9 different numbers. Okay, so I'm going to stop here, and this is the tablet. The rest is, I cannot do it for you, the rest. But if you have trouble with these, how to compute these, I can answer those questions if you have them. But see if you can get them, and we'll go from there. And then we'll have to call the direct solution, not with so many GZ1L to L, 3L, 4L, 5L, 6L. Yeah, too many. There'll be a lot fewer. I wish I would not have lost my solution. All right, so I'm going to stop here. And I suppose you all want an extension on the that would be wonderful. I'd like to give you also a time that you can actually ask questions. So maybe when is our next office hour? Is it Wednesday? What is date today? Today is 4/6. Tuesday. Today is Tuesday. Okay. So we have a office hour Wednesday. So if you have any questions on these, and I'm going to send this template to everybody that what I've done so far, and then you can ask me questions tomorrow, and then we'll push the deadline to I suppose Thursday then. Okay. All right, gentlemen, I'm gonna go and sleep now.